Hey there, class. We're here today. We're going to look at solving horizontal kinematics problems that involve constant acceleration. So let me scroll down here and we're going to get to our problem. And one thing that I'd like to kind of refresh our memory with is that we can describe situations in a variety of ways. We're going to see the description solved in words or in words. We are going to then draw a picture of that situation, and we are going to use equations to actually solve it. So from our four-pronged approach, we're going to be using the words, pictures, and equations in this particular video. In another video, we'll focus on the graphs. So let's get started. So here we go. We have a car accelerating along a straight road from rest to 60 kilometers per hour in 5 seconds. We want to know what is the magnitude of its average acceleration. All right, so I like to go through, read it once, get an idea of what's going on, and then I'm going to get an idea of what's going on here. So we have a car accelerating. All right, so that tells me something from the physics side of what's happening. We know that it's from rest. Okay, from rest tells me that velocity is 0. And I notice here, and then it goes to 60 kilometers. Oh, I meant to have a highlighter. Let's try that again. It goes to 60 kilometers per hour. So that's something that's happening. It sounds like to me that's happening later. And that's going to happen in, looks like, what, 5 seconds to do that. So let's scroll down here and see if we can show that we understand the situation using a picture. All right, so I'm going to just move this into place. And basically, again, what I see happening here is we have this car, and this car pretty much starts here. It's going to not be moving here, and it's going to move along, getting faster and faster and faster until 5 seconds. 5 seconds elapses, and we end up having some velocity over here. So as far as the picture goes, to show that I understand it here, I'm going to write down that it's 0 here, so 0 meters per second. Over here, there's some velocity, and it does actually have a velocity. It's going to be in this direction. Now notice I notice it doesn't say here, this is not a velocity as written in the problem, because it doesn't have a direction, but we can certainly give it a direction to make it a velocity, and that's what we're going to do. So that's going to be 60 kilometers per hour. And one other note here, that really when we talk about these problems, we're talking about the center of mass. That's this little blue kind of BMW shape that's inside the thing. So that's why my velocity is drawn directly above this. Also, something to note is that it's going to move from this position to this position right here. Okay, I don't know what just happened to my car over here. Let's see if we can fix that up. Okay, yeah, I'm not worried about it. But it moves in some change of position. That's what we call delta x. All right, that's what we call our delta x. And by the way, these are all vectors, so I'm going to put my vector symbol there as well. Let's go back to my problem. I don't see anything about this. So right now, this is a question mark. I also note that our goal here is to find the acceleration. Notice here it says, what is the acceleration? Okay, what is? In this case, the acceleration, it's getting faster, and that occurs between our two snapshots here. This is the goal of what I'm trying to do. All right, I am trying to find the acceleration. That is a vector as well. And note that it is drawn as a vector, specifically here, the acceleration vector. One last piece of information that we do know here is that it takes time of 5 seconds to get to this location. I guess our starting time, we could say, is going to be 0 seconds, because that's usually what we start a stopwatch at. As far as these snapshots go that we have in our picture here, we have this snapshot over here, but with what I would refer to as my initial or original, some people call it the original, initial snapshot. And then over here, the next time we're concerned about this car, is over here where this is what I'm going to call the final. All right. So we could give the subscript of 0 for original or initial. Some people, again, like to use an O or an I. And then over here, we're going to call this the final because these are instantaneous quantities. All right, I'm going to stop the video and summarize my knowns, my unknowns, and what I'm trying to find. I would ask that you do the same thing, stop the video, and see if you can summarize that in the known, unknown, and find section. So here we are picking up where we left off, and I've kind of summarized my knowns. I know that it's starting at rest. Rest means it's not moving. I know that it reaches a speed of 60 kilometers per hour. In fact, let's make a note here. This is a velocity, and velocity is a vector. Vectors must have something else associated with them. So let's go back to our picture here. There's something I didn't do, and this isn't overly important in usually horizontal kinematics, but it becomes extremely important when you deal with vertical. So I want to get into the habit of defining a direction. Okay, we could call this east if we want, but mathematically it makes sense to call this the positive direction. So I call this my reference arrow or my reference vector. But basically this tells me that anything that points to the right is going to be positive. As I note here, the velocity is pointing to the right. So when I go down here into the 60 kilometers per hour, to give it a direction, I want to make sure that I put that positive direction. That is the worst positive I've ever drawn. Let me try that again. How about that? That looks much better. Okay, then I also want to find the acceleration. That's the goal. In fact, what I'm really trying to find, if you read the problem again, it says magnitude. So really, I'm not all that concerned about the direction. So I'm going to put the little absolute value signs around it, telling me that I'm really just worried about the magnitude. I don't know how far it traveled, but I do know how long it took to do that. Okay, the next thing I like to look for is units. If I go back to the statement of the problem, I notice that the units, I want to say, yep, here they are right here. They want it in meters per second squared. So when I go down here, I want to make sure that all my units kind of agree with that. And I see right away, there's a red flag right here. Okay, this red flag, because of the units here of kilometers per hour, tells me that I do need to make a conversion. The meters per second here looks okay. Seconds here look okay as well. But I am going to definitely need to convert. So again, I'm going to do that off screen. And you, of course, can stop the video here. Try this conversion on your own, converting kilometers per hour into meters per second. Okay, so I've made my conversion. The purpose of this video is not to show you how that is done. Of course, I have other videos to show you how that's done, but basically I end up with converting the 60 kilometers per hour into meters per second, which I end up with the 16.7 meters per second. And of course, this is a vector, so I have the direction here as well. All right, next part of our problem solving is to come up with a strategy. And basically what we have here is that we are assuming constant acceleration. So if we assume constant acceleration, then that basically means that I can use kinematics equations. So what I need to find is basically a kinematics equation to get this. So we can use kinematics equations. Use kinematics, oh, I can't spell. Kinematics equations. All right, so I want to go over and I'm going to bring some kinematics equations onto the screen so that we can kind of narrow down what would work for us. So what I'm going to do here is narrow down my kinematics equations. As you can see, I've written down our kinematics equations here on the left-hand side. And our goal would be to figure out what equation would be the best one to do. So one of the first things I want to look for is I want to look for equations that have the thing that I want in it. And I can see right away there are two that do not work. This guy right here I'd get rid of because there is no acceleration in it. This one here is also has no acceleration in it, so I would get rid of that. All the other equations have an A in it, so they could be a possibility. All right, so I see an A in all these right here, here, and here. The next thing I would want to look for is, well, what's the easiest one? So I think this very first one that we have here seems to be a good one. Let's see if we do know what happened, or do we have the information that we need. So taking a look, delta V, we have that because that's just the change between here and here. All right, so we can figure out a change between these two. So we have that. So we can check that one off. And delta T is the time it takes to actually undergo this change of velocity. So I think this first equation is a good candidate to actually solve our problem. So I'm going to pick up down here in my implementation section. We're going to put in the numbers and we're going to solve it out. Okay, so one thing to note here, again, I said it a little bit ago, but delta V is a change in velocity, and that's a final minus an original velocity. Now, in our particular case, the final velocity is a number, but our original velocity is 0. So I like to make these simplifications early on before I actually substitute any numbers in. And I'm going to note here that the change in velocity is actually simply a final velocity. So we can make that same substitution pretty much into this equation over here. I'm going to substitute that in, and what I get is that my final velocity over my change in time is going to calculate my acceleration. So let's put our numbers in. We're going to substitute in some numbers here, and then we're going to solve it out with the math. All right, let me get myself some more room here, and basically we're going to put in the final velocity, which if I remember correctly was 16.7 meters per second, and my time, I believe, was 5.0 seconds. So when I do the math on that, I take 16.7 divided by the 5, and I'm going to get a 3.34 meters per second squared. And that is in the positive direction because, again, acceleration is a vector. Now, the response, my final answer is, or what I want to respond to the question, they wanted us to find the average acceleration, and it just said the magnitude. So all I'm really answering here is that for the acceleration, I'm going to write it not as a vector, so it indicates that it is simply the magnitude, is 3.34 meters per second squared. And so we'll highlight that as my final response to the question, and that's how we do it.